Hello, everyone. Welcome to our Deep Dive podcast, where today we'll be reviewing the paper Language Models Mostly Know What They Know by Saurav Kadavath and colleagues from Anthropic. Are you ready to explore how language models evaluate their own knowledge?
Absolutely. This paper is fascinating because it tackles a core question in AI. Can language models accurately assess the validity of their own answers? And, more importantly, can they predict when they actually know something versus when they don't?
That's right. The authors start by discussing the concept of calibration. In machine learning, calibration means that the probabilities a model assigns to its predictions should match the actual frequencies of those outcomes. For example, if a model says it's 80% confident, it should be correct about 80% of the time.
Exactly. And the paper shows that large language models, when given multiple choice questions in the right format, are actually very well calibrated. This means their confidence scores are meaningful. But I'm curious, what do they mean by the right format?
Good question. The authors found that if you present questions with explicit lettered answer choices like A, B, C, the models perform much better in terms of calibration. For instance, if you ask, "Who was the first president of the United States?" and give options A. Barack Obama, B. George Washington, C. Michael Jackson, the model can assign probabilities to each choice that closely match its actual accuracy.
That's interesting, so formatting really matters. But what happens if you change the format, like replacing an answer with none of the above?
The paper addresses that too. When they replaced an option with none of the above, both accuracy and calibration dropped significantly. The models seemed biased against choosing none of the above, even when it was the correct answer.
That's a valuable insight. It suggests that models are sensitive to how questions are structured. Now, moving on, the authors also explore self-evaluation. Can you explain what that means in this context?
Sure. Self-evaluation here means that after generating an answer to a question, the model is asked to assess the probability that its own answer is correct. This is called PE, the probability that the answer is true.
So, for example, if the model answers George Washington to the president question, it's then asked, is this answer true or false? And it assigns a probability to true?
Exactly. And the results are promising. Larger models, especially, are able to distinguish between their correct and incorrect answers using PE. Moreover, if you show the model several of its own generated answers before asking it to evaluate one, its self-evaluation improves even more.
That's like brainstorming multiple possibilities before making a judgment. It's a bit like how humans double-check their work by considering alternatives.
Yes. And the authors draw a parallel to self-consistency prompting, where models are encouraged to consider multiple solutions before settling on one. This approach helps the model better calibrate its confidence.
The paper also introduces another concept, PIK, or the probability that I know the answer to a question. How is this different from PIK?
PIK is about the correctness of a specific answer, while PIK is about the model's confidence that it can answer a question correctly, regardless of the specific answer. To train for PIK, the authors added a value head to the model, which predicts the likelihood that the model knows the answer.
That's a subtle but important distinction. PIK is more about self-awareness. Does the model know what it knows? How well did the models perform at predicting PIK?
The results were encouraging. When trained on a specific dataset, like Trivia QA, the models could accurately predict which questions they would answer correctly. Calibration was very good in distribution, meaning on data similar to what they were trained on.
But what about out-of-distribution generalization? Could the models predict PIK on new types of questions, like math or code, if they were only trained on trivia?
That's where things got interesting. The models showed some generalization, but calibration suffered. For example, a model trained on trivia could somewhat predict its knowledge on math or code questions, but its confidence scores weren't as reliable.
So there's partial generalization, but it's not perfect. The paper also explores how providing source materials or hints affects PIK. Can you elaborate on that?
Of course. The authors found that if you provide relevant background information, like a Wikipedia article related to the question, the model's PIK increases. This means the model recognizes when it has access to information that can help it answer the question.
That's impressive. It suggests that models can adapt their confidence based on the context they're given. What about mathematical hints?
Similar results. When given hints that lead toward the solution of a math problem, PIK increases. If the hints are misleading or irrelevant, PIK doesn't increase as much, or may even decrease.
That's a sign of nuanced reasoning. Now, the paper also discusses the impact of model size. How does scaling up the model affect calibration and self-evaluation?
Larger models consistently show better calibration and self-evaluation. As the number of parameters increases, both PI and PIK become more reliable. This trend holds across multiple tasks and datasets.
That's good news for the future of large language models. But the paper also mentions some limitations. For example, models fine-tuned with reinforcement learning from human feedback, RLHF, can become miscalibrated. How do the authors address this?
They found that simply adjusting the temperature parameter during evaluation can restore calibration in RLHF models. However, they caution that more intensive RL training might introduce calibration issues that are harder to fix.
That's a practical takeaway. Now let's talk about the broader implications. The authors use the term honesty as an umbrella for truthfulness, calibration, self-knowledge, explainability, and non-deceptiveness. How does this work contribute to building more honest AI systems?
By showing that language models can be trained to assess their own knowledge and calibrate their confidence, the paper lays the groundwork for more transparent and trustworthy AI. If models can reliably say, "I don't know," or "I'm not sure," users can make better informed decisions about when to trust AI outputs.
That's crucial, especially as AI systems are deployed in high-stakes settings. But the authors also note that their methods are limited to pre-trained language models and may not generalize to models trained for specific tasks or with different objectives.
Yes, and they highlight the need for future work to address scenarios where AI systems might know things that humans don't, or where models might be incentivized to behave deceptively.
That's a challenging area. Now let's discuss some of the technical details. The paper uses several metrics to evaluate calibration, such as expected calibration error, ECE, Breyer score, and AUROC. Can you briefly explain these?
Sure. ECE measures the average difference between predicted probabilities and actual outcomes. A lower ECE means better calibration. The Breyer score combines accuracy and calibration into a single metric. Lower is better. AUROC, or area under the receiver operating characteristic curve, measures the model's ability to discriminate between correct and incorrect answers, regardless of calibration.
Thanks for clarifying. The authors also experimented with different evaluation tasks, including multiple choice, true-false, arithmetic, code synthesis, and story completion. Why is this diversity important?
Evaluating across diverse tasks ensures that the findings aren't limited to a single domain. It also tests the model's ability to generalize its self-evaluation skills to new types of problems.
That makes sense. The paper also compares different methods for discriminating what models know, such as using entropy or loss. What did they find?
They found that while entropy and loss can provide some signal about whether a model knows the answer, these methods aren't as robust as directly training for PIK. In particular, as models get larger and more capable, they can generate diverse but correct answers, making entropy less reliable.
That's an important nuance. Now let's talk about the practical implications. How can these findings be used to improve real-world AI systems?
One application is selective prediction, where a model abstains from answering questions it's not confident about. This can reduce the risk of AI systems making confident but incorrect statements.
That's valuable for safety and reliability. The authors also mention that their methods could help identify and correct failures of honesty in deployed systems. Do you think this approach could be integrated into current AI products?
Definitely. By incorporating self-evaluation mechanisms, AI systems can provide users with confidence scores or even flag when they're unsure. This transparency can build trust and help users make better decisions.
That's a promising direction. The paper also discusses the relationship between learning and in-context learning. Can you explain what they mean by that?
The authors observe that models trained to predict PIK for standalone questions generalize in such a way that PIK increases when relevant information is provided in the context. This suggests a connection between the model's long-term memory and its ability to use information presented in real time.
That's a deep insight. It hints at how models integrate prior knowledge with new information. Now let's touch on the limitations the authors mention. What are some areas where more research is needed?
The authors note that their work is limited to pre-trained language models and doesn't address models fine-tuned for specific tasks. They also acknowledge that their methods may not prevent intentional deception, especially if models are incentivized to maximize human preference rewards.
That's a critical point. As AI systems become more advanced, ensuring honesty and transparency will require ongoing research and new techniques.
Absolutely. The authors also suggest that more work is needed to study generalization across a wider range of tasks and to understand how honesty extrapolates to new contexts.
Before we wrap up, let's summarize the key contributions of the paper. First, large language models can be well calibrated on diverse multiple-choice questions when formatted appropriately.
Second, models can self-evaluate the correctness of their own answers using PIK, and this ability improves with model size and when given multiple samples to consider.
Third, models can be trained to predict PIK, the probability that they know the answer to a question. And this skill generalizes to some extent across tasks and in the presence of relevant context or hints.
And finally, these findings lay the groundwork for building more honest, transparent, and trustworthy AI systems by enabling models to assess and communicate their own knowledge and uncertainty.
Well said. This paper is a significant step toward AI systems that not only generate answers but also know when they're right and when they're not.
That's all for today's episode. We hope you enjoyed this deep dive into language models mostly know what they know. If you have questions or want to suggest future papers for review, let us know.
Thanks for listening, and remember, the best AI is not just smart, but also honest about what it knows. See you next time.
To summarize, this paper demonstrates that large language models can be well calibrated, can self-evaluate their own answers, and can be trained to predict when they know or don't know the answer to a question, laying the foundation for more honest and trustworthy AI systems.